So here we have two cylinders that are wrapped in a wire. And in the cylinder on the left, either end of the wire is attached to a resistor. For the cylinder on the right, either end of the wire is attached to a battery and to a switch. Now, the moment we close the switch, the current will go from 0 in this wire to something greater than 0. And as a result of that, we will have an induced current flowing through this wire. And the question is, for the resistor attached to the wire that is wrapping around the cylinder on the left, will the induced current through this resistor flow to the right or to the left? So this is going to be a good application as a practice problem of Lenz's law. So let's think about what goes on in this problem. Now, Lenz's law states that we want to always keep the magnetic flux the same. So nature will oppose a change in magnetic flux. So right now, at this moment in time, the switch is open, so there is going to be no current flowing through the circuit. But I could close the switch, and the moment I close the switch, current will go from 0 to something bigger than 0. So the current in this circuit is going to increase. So I will have a current flowing through this circuit that is bigger than nothing. Now, the way the circuit is drawn, as I said, the wires in the cylinder come out of the board, the current will flow upward, and then the current will flow into the board when you're above the cylinder. So in each of these wires, the current will be flowing upward. So my current I, as it flows through the wire that's wrapped around the cylinders, the current I is flowing up when it's in front of the cylinder, closer to you. The current will be flowing down when, from your perspective watching this video, when the wire is behind the cylinder. Okay, well, a current flowing through a wire will create a magnetic field. Flowing through this wire will create a magnetic field. Okay, so what direction will the magnetic field point in this region over here? So I could apply the right-hand rule. The wire wraps around a cylinder, so the wire is roughly in the shape of a circle. So the wire is going to be the curly part for my right-hand rule. Now, the curly part points upward, so I want my 4 fingers to be pointing upward when they're in front of the cylinder or downward when they're behind the cylinder. In both of those cases, my 4 fingers are pointing up when they're in front of the cylinder from your perspective, and the magnetic field, due to this current, is going to be pointing to the left. So the magnetic field created by this current is pointing to the left. So I could say that the magnetic field B went from 0 to something bigger than 0. Pointing to the left. Now, I could look at the structure of the magnetic field created by a solenoid, and I know the magnetic field is going to wrap around, but the important thing is, at the location where this cylinder is found, the magnetic field is still going to be pointing to the left, more or less. Now, the magnetic field does tend to spread out, so the magnetic field will not be purely left. It'll be slightly angled, and then the magnetic field will wrap around and come back in this way. But roughly at the location of the cylinder, the magnetic field created by this current is pointing to the left. So this is my original magnetic field. So this is the magnetic field I'm just going to call B. Now, from this cylinder's point of view, the magnetic field went from 0 to something bigger than 0. So from this cylinder's point of view, the magnetic field increased, and as a result, the magnetic flux increased. Lenz's law says nature will oppose a change in magnetic flux. So Lenz's law, if the magnetic field through the cylinder was 0, now it's something bigger than 0 pointing to the left, Lenz's law is going to try to keep the magnetic field practically 0. Because when the magnetic field through the cylinder is 0, the magnetic flux through that cylinder will be 0 as well. So Lenz's law will try to keep the magnetic flux equal to 0. It's not going to succeed, but it's going to try to keep the magnetic flux 0. The way Lenz's law will keep the magnetic flux 0 is by creating a second magnetic field that tries to cancel this magnetic field that is increasing. So the induced magnetic field is going to attempt to cancel this magnetic field. So I could say the induced magnetic field which I will call B induced, will attempt to cancel the growing magnetic field from the current flowing on the right, created by the current in the circuit on the right. So B induced is going to point to the right. So we have two magnetic fields. We have the magnetic field created by this current, which is B that I drew in red. Then we have B induced, which is the second magnetic field that I drew here in purple. Now, there are two things I want to emphasize right now. Lenz's law says nature opposes change. So the induced magnetic field will not always attempt to cancel the original magnetic field. The new magnetic field will always attempt to keep the original magnetic flux unchanged. So this magnetic field went from 0 to something bigger than 0. Well, B induced wants it to be 0 again. So in this scenario, B induced will point to the right. But in the opposite case, if we had a really large original magnetic field pointing to the left, and then we opened the circuit, well, if we open the circuit, the current will stop flowing, the magnetic field will turn off. Well, nature opposes that change, so nature will try to keep the magnetic field big. So B induced will not always try to cancel the magnetic field. B induced will attempt to prevent a change in magnetic flux. In this scenario, it turns out that B induced will attempt to cancel because the original field is, but that's a result of the original field was 0, and B induced wants to keep it at what it was, keep the magnetic flux at 0. The other thing I want to emphasize is the induced magnetic field will not completely cancel B. Nature is not going to be able to fully prevent a change in magnetic flux. Nature is just going to attempt to prevent a change in flux. So nature will ultimately not succeed in keeping the magnetic flux at 0. It will be something, but it's going to try. So at this point, like I said before, we have a curly part and a straight part, and we're going to use the right-hand rule to determine ultimately the direction of current through the circuit. So in this case, the wire is in a circular pattern, so the wire will be the curly part that corresponds with my 4 fingers. Because I assigned a direction to current, basically the direction of the wire, the direction of the magnetic field automatically becomes my thumb. So I know the induced magnetic field is going to point to the left. So I will write that as B induced points to the right, That is going to be my thumb. Well, as a result of that, the direction of the current is automatically going to be chosen for me. So from the right-hand rule, my fingers will be pointing down if they are in front of my thumb. So my 4 fingers point down when they are in front of my thumb. So in this case, the current flowing through these wires wrapped around the cylinder is going to be down in front of the cylinder. And if I follow through, the current will flow like this, and I find that the current flows to the right through the resistor. So again, I really want to emphasize that the direction of B induced, it's not that B induced attempts to cancel B original. B induced attempts to keep B original, keep the flux the same. So if B original goes from small to big, B induced will oppose because it keeps it small. If B original goes from big to small, then B induced opposes change. So B induced would try to keep B big, and in that scenario, B induced would have pointed the same direction.